Okay, thanks. Well, hello, my name is Dave Miller, and this afternoon I am going to present my project on building a high data rate QPSK 15 megabit per second real-time GNU radio modem using just multi-cores of a general purpose processor in parallel. No FPGAs or graphics processor units are required to get up to this data rate for this project. So first, some background. Last year at the 2021 conference, I did provide a paper and talk on building really just a prototype modem to see if this was feasible at BPSK with 10 megabits per second. This year I have an improved design with QPSK up to 15 megabits per second. I also created a GitHub site for all the documentation. Also the out of tree code that's needed, test files, prepared files, and flow graphs. So basically, because of the stagnation of Moore's law in a single core, the chip industry, I really think, has moved forward with Moore's law via multi-cores. So I think we need to take advantage of multi-cores if we really want to increase the data rate capability of a GNU radio modem with just software. So for example, flow graphs and designs that take advantage of these multi-cores by putting them in parallel. So the purpose is to build a radio that can operate well beyond 6 megabits per second with GNU radio. Basically a design that uses multi-cores in parallel. Basically, it would break up the IQ stream coming in into overlapping chunks, basically the incoming stream from the dongle. Then it would process those chunks in parallel cores of the GPP. Then at the end, the trickiest part really is to restitch these parallel streams coming in back together again into the original transmitted frame stream. And we don't want any missing bits or missing frames, and we don't want any duplicates bits or duplicate frames due to this overlapping approach. So the scope exactly is 15.0 megabits per second for this project, and this modem, QPSK, at 15 megabits per second, the parallel multi-core approach. I used an inexpensive, low-cost Lenovo laptop with 8 cores. I used the GNU Radio 3.10.3 for this, the Ubuntu operating system, and a low-cost Lime SDR mini dongle. And that had a USB 3.0 interface for good speed. I did some test loops at 80 megahertz, and you can see the test configuration for those tests, those loop tests at the bottom of this chart. And again, here's the GitHub site, design documents on there, flow graphs, relevant files like prepared test files, and of course the out of tree code. So this provides a flow graph, one flow graph for the whole modem, transmit and receive. I know the text is very small here, but what I'm going to do is zoom into pieces of this in later charts. But basically, the demodulator portion has 3 parts: the front end, the parallel synchronization chains, and a back end. Note for the out of tree blocks at the bottom of this figure, that is the only part that required out of tree blocks. I tried to use in tree blocks as much as I could, except for the bottom part, which at the end, which is the tricky part, restitching everything back together again. And again, the GitHub site there with this flow graph and design documentation and test files is available. Also, I put together a paper for the conference, so you can see the paper that goes with this project also on the proceedings. Okay, I'm zooming into the test modulator now. That was at the top of the previous flow graph. What I used here was just a pre-modulated complex IQ file. I put it in the file source and transmitted that out. I did this just so the modulator only required 1 core for this project, and that left me with 7 more cores for the demodulator portion. The pre-modulated complex file that I used is also on the GitHub site. Okay, the first part of the demodulator, the front end, I'm zooming into that right now. Again, no out-of-tree blocks. Basically, what this part of the demodulator does, it breaks the incoming complex IQ stream into parallel overlapping chunk streams, the incoming single stream from the Lime SDR Mini. And then what it does is it adds a 1524 sample fixed pattern chunk preamble. And I'll talk about the chunks in more detail in the later charts. And the chunk preamble is added to each chunk so that I can go ahead and restitch these streams back together again. The chunk preamble is a key part of that. It has a marker in there to identify the different chunks downstream. That 1524 fixed pattern of samples is also on the GitHub site. And you could plug that into the file source block at the top of this flow graph in the middle. Okay, this is the demodulator front end again, but with a functional view. The top rectangle is the incoming stream of samples from the dongle. I chopped those up into chunks with a 12,000 sample overlap at the beginning of each chunk. So 12,000 sample overlap from chunk to chunk. And you could see that here in the figure in the 202, 206, and 209 of this figure. And I'll talk about that overlap more and the reasons for it in a couple charts. Okay, this is another functional view of the front end, but the second half where the chunk preamble is added to the beginning of each chunk. Each chunk is 82,000 samples. The chunk preamble is added to the front of each. So the chunk preamble has three parts. The first part is 960 bits, basically 1, -1, 1, -1, but in complex format. The next part is of the preamble is the marker. That's 64 samples. And again, the marker is used downstream to identify the beginning of each chunk so we can later put things back together again, restitch them. And the third part is just some 500 fill zeros. Okay, this is the second part of the demodulator, the parallel synchronization chains. Please read this right to left. And basically I have three chains for 3 chunk streams. This is where I do the parallel portion of the demodulator to get the speed way up. The symbol sync tends to be the bottleneck for a QPSK or BPSK modem with GNU radios. So trying to put those in parallel and do 3 of them at the same time. So the overlap, the reason for it here is that the symbols per every 82,000 chunk of samples could be a few symbols different for every 82,000 samples, maybe two samples per bit or per symbol, 41,000, but you might get 41,001 or 39,999 for another as it flows through the system. So we have some overlap there. Plus, every chunk that goes through, the symbol sync causes loop have to resync 2 times, one for the preamble and one for the chunk itself. So you lose bits or you get error bits during that sync process. So we need some overlap so we don't lose anything. Okay, this is the last part of the demodulator. This is the one that requires all the out-of-tree blocks or many of them. This is the back end. So basically, this part of the modem restitches those 3 parallel chains back together again into the original transmitted frame stream with no errors. These are the list of the blocks I use for out-of-tree. They're on the GitHub site also. I tried to really use even in-tree blocks for this and just modify them a bit and recompile them. For example, to look for a marker that might have 4 phases due to QPSK ambiguity, 45, 135, 225, and 315. I just used the correlate access code block that comes in the in-tree, but I modified it so it could look for 4 marker patterns for each of the different possible phases. Okay, this provides this chart a functional view again of the demodulator back end, the front part. What the blocks do is they identify the beginning of each chunk in the 3 different chains. I extract each chunk, and then I put all these chunks from the 3 streams back together again in a single stream. Everything's in order again, but the overlap still exists. We still need to handle that part. So that the second half of the back end and the last part of the modem, the demodulator really, read this right to left. We use the distance between ASM markers. If you look at 510 here in the figure above, if it has 4,192 bits, which is the frame length I'm using, the correct frame length, I pull it out, extract it, it continues on downstream. If the distance between markers is more than 4192, I identify that as some bad overlap bits, we pull it out. If it's really, that would be 511 in this figure. 507, if there's just a few bits between the markers, that I have to delete those bits, and also the frame after it, 508, even though it might be the correct 4192, as a duplicate frame. So those that are good are going downstream to the final part, which is the resolve phase block. And basically what I do there is I look at the bits in the ASM of the frame, look for the rotation. There'll be 4 possible patterns there due to the QPSK ambiguity. And then I rotate the bits in the data field of the frame as required to match the ASM rotation. So everything coming out now should be the original frame stream that was transmitted, no duplicate bits, no duplicate frames, no errors in the bits. So what I did here is I took advantage of the built-in affinity setting that GNU Radio already has to assign the blocks to the cores. And that was very helpful, this GNU Radio affinity setting that's already available in every block. For example, the shaded rows here for the 3 parallel chunk chains for the symbol synchronizer and Acostas loop went to cores 4, 5, and 6. The core number is on the right column. The name of the block is in the left column. So the results in future work, this is the last chart. Basically, I was able to operate up to 15 megabits per second. I ran it maybe for about 15, 20 seconds. That test file is on the GitHub site also. It, of course, becomes a very big file very quickly, but the demonstration was working well. I brought stuff with me, so maybe during the conference, if anyone's interested, I could get this thing up and running with the Lime SDR if there's an interest. Also, the paper that goes with this project for the conference has a lot more details also. And the GitHub site, again, has the outer tree code and more details and prepared test files. I also put a simulation flow graph into the GitHub site. So if you don't have a dongle and you got 8 cores in your general purpose processor PC, you could still run this, and you should get to about 15 megabits per second. If you don't have 8 cores, only a few cores, you should still be able to run this. You'll just have to lower the data rate and not expect it to run as fast. So the future work, I think this is scalable to even higher data rates. Just add more cores, add parallel chains, add more of them. If I had 16 to 24 cores in a PC, and I think maybe that will be available with consumer desktops, or at least 24 cores maybe in the next year. You can add some coding and maybe do that in parallel, put together a real-time modulator, which might take a few cores to do, and higher data rates. So that pretty much is it. So everyone, well, thanks for your time.
I didn't see any questions from the internet about this, but similar to the last talk, were there any features that you found missing in GNU Radio that should be added to make future work on projects like this simpler?
I'm sorry, what was that? That's from the internet?
There were no other questions from the internet, but we have one question from the room here.
Oh, okay, I wasn't sure where it was coming from.
So just a quick question. Have you tested this at low SNR values, and does it tolerate, that kind of performance or not?
Low SNRs, like if I were using coding and you were operating.
Low levels on your signals, low signal levels.
Yes, I have put noise into this, and I could demonstrate that. I do have a noise block. I didn't show that in the flow graph. I have some, so I did test it at noise and kind of see how it performed when you're getting down there where some bit errors are popping up. Yes.
That's it. When using the symbol synchronization block, how did you, the recommended route is to empirically find those values unless you do a lot of research into what you're developing. So how did you match the symbol sync block to match your needs? What research did you do and how did it contribute to that block?
Okay. Yeah, I've used the symbol synchronizer before. Oh, I'm sorry, I'm not close enough to the mic. I have used the symbol synchronizer before and have looked for good parameters. I think some other folks have already done some also in past conferences, some good settings for that. I know, I don't know if Daniel Estevez is here. I know his GR satellites is a great area. And I think he did like one or two conferences ago, a really good tutorial on setting up a lot of these blocks. So yes, it was a little trial and error getting that up and running first a few years ago when I first started using it. I didn't, it wasn't obvious. So hopefully there is some material on that from the past conferences. I did a talk 3 conferences ago where what parameters I found useful for that. And you can go to the flow graph on the GitHub site and you can see everything that I used to set it up. So if you just use those parameters, it should work for most cases, I think.
Cool. Similar question. I think your setup had a similar clock or the same clock for transmit and receive. Have you tested it with Doppler or like changing phase offset and time offsets?
I didn't put any Doppler into this. So to really make this work with Doppler, like if you had a LEO spacecraft where you're moving along at a couple hundred hertz per second, you would have to put some blocks in the front of this to, even if you were doing something low data rate that's not in parallel, to kind of compensate for that Doppler. I have looked at that, and I do have something that that's up and running and working kind of on the side for a low data rate flow graph. So if you're interested, I could probably show you that offline. But you would need to compensate. You would need to maybe take an FFT of where your center frequency is, keep updating that, send that update into an entry block that does the sine, puts out a sine wave in complex form, and keep updating that based on your FFT to kind of keep yourself centered for the symbol synchronizer block. So it never sees that change is the way I've seen maybe a possible path forward for like LEO Doppler.
Okay. Yeah, there might be a little bit of a different shift across each of the branches that's doing the parallel processing. So when you go to stitch it back together, it could be problematic even if you compensate up front, I think. But it'd be good to, for future work, add 2 clocks at least for transmit and receive.
I'm not quite sure I heard the question exactly.
Oh, the comment was it might be good for future work to add 2 clocks, one for transmit and one for receive. And
one for transmit and receive, kind of split this flow graph up. Yeah, that would probably be the best way forward. To operate the Lime SDR, I really needed just one. I don't think I could operate the one dongle with 2 flow graphs, so I stuck the modulator one in there. So that would work well. I'd probably just need 2 dongles to do that, maybe 2 Lime SDRs, one for a flow graph controlling the transmit one and one the receive. And as long as you have enough USB ports on your laptop or desktop, it would be a good way to go, sure.
And the last question goes to the internet. Which single block would gain most from hardware acceleration?
Which block? Definitely the symbol synchronizer is the block that's the most processing intensive And that's why I need to go to, it's the bottleneck on the processing. If you just have that with one core, it's the limiting factor with that, without doubt.
Thank you. All right, let's give one more big hand for this talk.